The formulation of the conservation equations for the flow across a normal shock wave resulted in the 6 equations labelled 1 to 6 here. Now we're going to combine these equations, and this will lead us to finding an expression for the density ratio across the discontinuity in the flow. So that'll be rho 2 over rho 1. We'll then be able to find out how the pressure and temperature of the flow change across the shock wave. So let's get started. Just move the screen down. We'll begin by looking at equation 2. So let's try rearranging equation 2. And what we're going to do, so that came from the momentum equation, so we had the difference in pressure related to the change in density and velocity, and we're going to divide equation 2 by P1. So we get, and I'll write it this way, P2 over P1 minus 1 is equal to rho 1 V1 squared over P1 minus rho 2 V2 squared over P1. And let's write this as, okay, so we've got we'll leave the P2 over P1 minus 1 on the left hand side. On the right hand side I'm going to start off, just multiply top and bottom by gamma. Then I'm going to take a rho 1 V1 squared outside of what's left, rho 1 V1 squared over P1, and that leaves us with, we've taken that out of our brackets, and we're going to get our rho 2 V2 squared over rho 1, actually I'm going to write this as V1 V1, and I might just write the top as V2 times V2. Okay, so we've got that. Now what we're going to do is just try to identify a couple of things in there. So remember that gamma p over rho is the speed of sound squared. So we had that in equation 6 up here. So let's see in here we've got gamma p over rho on the bottom. So that'll be a 1 over a1 squared. The other thing I've got is I'm just going to pick out, the reason I separated the V2 squareds and the V1 squared is because a rho V from our continuity equation, equation 1 up here, is that rho 1 V1 is equal to rho 2 V2. So that can go out. So we can say from equation 1. Now, the other thing we'll note is, let's just note that V2 over V1 is equal to rho 1 over rho 2 from equation 1 also, just rearranging equation 1. So using those, we can say, therefore, how our pressure changes, P2 over P1, can be written as 1 plus, so we're taking the 1 over to the right hand side, we've got a gamma in here. Now we've got a V1 squared over an A1 squared, which is just our M1 squared, velocity over the speed of sound, and we're left with this 1 minus, and we've got, we're saying that the V2 over V1 is rho 1 over rho 2, so that's going to be minus rho 1 over rho 2. And we'll call that equation 7. So I'll just note in here, just for completeness, since our M1 squared is equal to V1 squared over A1 squared. So we've got that expression there. We've called that equation 7. Next thing we're going to work on is our energy equation. So I'll just slide the page up for now. and look back at our energy equation, which is up here, equation 3, which said that the total enthalpy was conserved across the shock wave, and that the total enthalpy is the static enthalpy plus a half V squared. So we're going to work on that now, and we're also going to note from equation 5 that we can say H is equal to CPT. So putting those two things together, we're going to get another expression. So slide us back down again. And let's say we'll work now on the energy equation. Which is our equation 3. And we'll note that we can relate the static enthalpy to the specific heat and the static temperature from what we called equation 5. So therefore, when we take that, our H1, which is CpT1, plus our half V1 squared, which is the left-hand side of equation 3, is equal to H2, which is CpT2, plus a half V2 squared. And now let's write this as, see if we can get a temperature ratio out of this. So we can divide everything by Cp, and we'll move the T1 and the T2 together. So we'll end up with saying that T2 over T1 is equal to 1 plus a half V1 squared over CpT1 minus a half V2 squared over CpT1. So essentially, to get that, we've divided everything by CpT1, and then we brought the T2 and the T1 together. So we've got that. Let's take that a little bit further and say that this is 1 plus, let's take a half V1 squared over CpT1 out of this, a half V1 squared over CpT1, and we'll say we've got one of those minus, we're going to get a V2 over V1 squared coming out in there. And let's say that that is going to be equal to 1 plus, now I'm going to write this as gamma minus 1 over 2 m1 squared times 1 minus rho 1 over rho 2 squared, and call that equation 8. Now, in order to get from what we had here down to this expression here, there's a couple of things. So we can do this because, first of all, the V2 over V1 is equal to rho 1 over rho 2. So that came from our continuity equation, which said that rho 1 V1 is equal to rho 2 V2. And we've also used here that A1 squared is equal to gamma R T1, so relating the static temperature, the speed of sound to the static temperature through gamma and R. And there's one further thing we've done in order to get that. We've got a relationship between the specific heats and gamma and R, and Cp can be written as R times gamma over gamma minus 1. So you might want to play around with that and see if you can demonstrate that. It's a few lines. Okay, so that's left us with an expression for the temperature ratio across the shock wave. Let's take a little bit further and let's say from our perfect gas relationship, P equals rho RT, we can also get an expression for T2 over T1. find T2 over T1. So we can write that as T2 over T1 is equal to P2 row 1 over P1 row 2, and this is just using P is equal to rho R RT. Okay, we'll call that equation 9. So we'll keep going now. So we've got a couple of expressions for T2 over T1 coming out there now. Let's use equation 7, which is at the top of the page here, our pressure ratio. Let's say 7 gives us P2 over P1. So we can put our expression 7 into expression 9 because we've got a P2 over P1 coming up in there, and that gives us an expression that T2 over T1 is equal to squiggly brackets 1 plus gamma m1 squared 1 minus rho 1 over rho 2 all times, so that's our expression for P2 over P1 from 7, and then we're left with our rho 1 over rho 2, and we'll call that equation 10. And we'll just slide the screen down a little bit. Now there are two expressions for T2 over T1, one from up here in equation 8 and one here in equation 10. Let's equate the expressions for T2 over T1 between 8 and 10. So starting with equation 8 and writing it in this form here, just expanding it a little bit, we get 1 plus gamma minus 1 over 2 m1 squared minus gamma minus 1 over 2 m1 squared times rho 1 over rho 2 all squared. And that must equal what we get from equation 10, and we'll write that in this form. 1 plus gamma m1 squared times rho 1 over rho 2 minus gamma m1 squared times a rho 1 over rho 2 squared. If we now look at what we have in this expression, we'll see we have some terms with rho 1 over rho 2 squared in them. We have a term with rho 1 over rho 2 in it, and we have a term with neither of those in it. So we have here a quadratic in rho 1 over rho 2. So we can write this by collecting those terms together to obtain this quadratic equation. And this is the form that we end up with. So here's functions of just gamma and m1 times a rho 1 over rho 2 squared, functions again of gamma and m1 of rho 1 over rho 2, and then another function of just gamma and m1. So we have a quadratic in rho 1 over rho 2, and the only parameters we've got are gamma and m1. I'll slide the screen down again. For a quadratic equation, we'd expect two solutions. The first solution that we get out of this is that rho 1 is equal to rho 2. So no change in the density across this shock wave, so basically nothing happening. So this is a trivial solution. The more important one, and the one that we're interested in, is this expression for rho 1 over rho 2 being 2 plus gamma minus 1 m1 squared over gamma plus 1 m1 squared, and we'll call that equation 11. So we now have an expression for rho 1 over rho 2 from equation 11. Once we have rho 1 over rho 2, if I just slide the screen up, equation 8 was an expression for T2 over T1, and that came out in terms of gamma m1 squared and rho 1 over rho 2. So we can put our expression for rho 1 over rho 2 to get an expression for T2 over T1. So put equation 11, our expression for rho 1 over rho 2, into equation 8, our expression for T2 over T1, and that will give us an expression for T2 over T1 in terms of gamma and m1 squared. And now look up at equation 9, which had T2 over T1, P2 over P1, and rho 1 over rho 2 in it. So now we have expressions for T2 over T1 and for rho 2 over rho 1, so we can put those into that expression 9 and get an expression for the pressure ratio across the normal shock wave. So I write that we can put equation 11 also in equation 9 to give us how the static pressure changes across a normal shock wave. You might like to try putting in those expressions to obtain relationships for T2 over T1 and P2 over P1. In the next video, I'll put the equations up and I'll also show you how to determine the Mach number of the flow downstream of a normal shock wave.